Welcome back, everyone. In the previous lesson, we learned the 5 major types of machine learning: supervised learning, unsupervised learning, semi-supervised learning, self-supervised learning, and reinforcement learning. But here's an important question. Imagine you build a machine learning model. How do you know whether it's actually good? What if your model gets 95% accuracy, but still makes terrible decisions? Today we're going to answer exactly that. In this lesson, we're diving into model evaluation, the techniques that data scientists use to measure whether a machine learning model is performing well or not. By the end of this video, you'll understand the most important evaluation metrics used in both classification and regression problems, along with concepts like cross-validation, overfitting, underfitting, bias, and variance. Let's get started. Here's our roadmap for today's lesson. We'll start with classification metrics, where we'll learn about accuracy, precision, recall, F1 score, and the confusion matrix. Then we'll move to ROC Curve, AUC, and log loss, which help evaluate probability-based predictions. After that, we'll switch to regression metrics, including MAE, MSE, RMSE, and R-squared score. Then we'll learn how professionals test models using cross-validation, K-fold, and stratified K-fold. Finally, we'll finish with some of the most important concepts in machine learning: bias, variance, underfitting, and overfitting. These concepts appear in almost every machine learning interview, so pay close attention. Before we can understand any classification metric, we first need to understand the confusion matrix. Think of it as the report card for a classification model. It contains 4 possible outcomes. First, true positive. The model predicted yes, and the actual answer was also yes. That's a correct prediction. Second, false positive. The model predicted yes, but the actual answer was no. This is also known as a false alarm. Third, false negative. The model predicted no, but it should have predicted yes. In other words, it missed something important. Finally, true negative. The model predicted no, and the actual answer was also no. Let's make this more practical. Imagine we're building a spam filter. If a spam email is correctly identified as spam, that's a true positive. If a normal email is mistakenly sent to the spam folder, that's a false positive. If spam reaches your inbox, that's a false negative. And if a normal email stays in your inbox correctly, that's a true negative. Almost every classification metric you'll ever learn is calculated using these 4 numbers. Now that we understand the confusion matrix, let's calculate some useful metrics. The first one is accuracy. Accuracy simply answers the question, out of all predictions, how many were correct? It's the easiest metric to understand, but accuracy isn't always enough. Imagine a disease detection model where only 1 out of every 100 patients actually has the disease. If the model predicts healthy for everyone, it'll still have 99% accuracy. But it's actually useless because it never finds sick patients. That's why we also need precision. Precision asks, when the model predicts positive, how often is it correct? High precision means very few false alarms. Then comes recall. Recall asks, out of all actual positive cases, how many did we successfully detect? High recall means we rarely miss important cases. Using the email example on the slide, out of 100 emails, there are 20 spam emails. The model flags 25 emails as spam. Among those, 18 are actually spam. So the precision becomes 72%, while the recall becomes 90%. Different applications prioritize different metrics. For example, spam detection may prioritize precision, while disease detection often prioritizes recall. F1 score. Sometimes focusing only on precision or only on recall can be misleading. That's where the F1 score comes in. The F1 score combines precision and recall into a single number. Instead of taking their normal average, it uses something called the harmonic mean. Why? Because the harmonic mean heavily penalizes imbalance. Suppose your precision is 100%, but your recall is only 10%. A simple average would still look decent. But the F1 score will be low because one metric is performing poorly. Think of precision and recall as two people on a seesaw. If one side is much higher than the other, the seesaw isn't balanced. The F1 score rewards balance. It's especially useful when dealing with imbalanced datasets, where one class appears much more often than the other. Now let's move beyond simple metrics. Meet the ROC curve. ROC stands for Receiver Operating Characteristic. Don't worry about the long name. What's important is what it shows. The ROC curve plots the true positive rate against the false positive rate at different decision thresholds. A perfect model stays close to the top left corner. A random guessing model follows the diagonal line. To summarize the entire curve into one number, we use AUC, which stands for area under the curve. AUC ranges from 0 to 1. An AUC of 1 means perfect classification. An AUC of 0.5 means your model performs no better than random guessing. Generally, the higher the AUC, the better your model separates different classes. Sometimes we don't just care whether the prediction is right or wrong. We also care about how confident the model was. That's exactly what log loss measures. Imagine two models both predict the wrong answer. The first model was only 60% confident. The second model was 99% confident. Which mistake is worse? Obviously the second one. Log loss heavily penalizes predictions that are confidently wrong. That's why lower log loss is always better. A perfect model has a log loss of 0. This metric is commonly used when models output probabilities instead of simple yes or no predictions. Everything we've discussed so far was for classification problems. Now let's switch to regression, where the goal is predicting continuous values like house prices, temperatures, or salaries. The first metric is MAE, or mean absolute error. It calculates the average error between predicted and actual values. It's simple and easy to understand. Next is MSE, mean squared error. Instead of taking the absolute value, it squares every error. This means large mistakes become much more expensive. That's useful when we want to punish big prediction errors. Then comes RMSE. It is simply the square root of MSE. The advantage is that RMSE has the same unit as the original data, making it easier to interpret. Finally, we have R-squared score. Instead of measuring error directly, R-squared tells us how much of the variation in the data our model can explain. An R-squared value close to 1 means the model explains most of the variation. The closer it is to 0, the less useful the model becomes. Let's say you split your data once into training and testing sets. What if you accidentally got a lucky split or an unlucky one? Your evaluation might not represent real-world performance. That's why we use cross-validation. Instead of testing once, we test multiple times using different data splits. The most common method is K-fold cross-validation. Here's how it works. We divide the dataset into K-equal parts. For each round, one fold becomes the testing set. The remaining folds become the training set. We repeat this process until every fold has been used as the testing set exactly once. Finally, we average all the results. This gives us a much more reliable estimate of model performance. Regular K-fold works well in many situations. But what if your dataset is highly imbalanced? Imagine a fraud detection dataset where only 1% of transactions are fraudulent. A random split could accidentally place almost all fraud cases into one fold. That would produce unreliable results. This is where stratified K-fold becomes useful. Instead of splitting randomly, it preserves the same class proportions in every fold. Each fold contains nearly the same percentage of positive and negative examples. That's why stratified K-fold is the preferred choice whenever you're working with imbalanced classification datasets. Now let's talk about two concepts that every machine learning engineer must understand: bias and variance. Bias measures errors caused by overly simple assumptions. High bias means the model is too simple and cannot capture important patterns. Variance measures how sensitive the model is to small changes in the training data. High variance means the model changes too much depending on the data it sees. The ideal model has low bias and low variance. If bias is high, predictions are consistently wrong. If variance is high, predictions become unstable and inconsistent. The goal in machine learning is finding the right balance between these two. Bias and variance lead us to one of the most important topics in machine learning: underfitting and overfitting. Underfitting happens when the model is too simple. It fails to learn important patterns. As a result, it performs poorly on both the training data and new data. Overfitting is the opposite. The model becomes too complex. Instead of learning general patterns, it memorizes the training data, including its noise. It performs extremely well during training, but struggles when tested on unseen data. The sweet spot is called a good fit. The model learns meaningful patterns while still generalizing well to new data. If your model underfits, try using a more complex model or adding better features. If it overfits, try collecting more data, simplifying the model, or using regularization techniques. Let's quickly recap what we've learned today. We started with the confusion matrix, which forms the foundation of classification evaluation. Then we learned accuracy, precision, recall, and the F1 score. After that, we explored ROC curves, AUC, and log loss to evaluate probability predictions. For regression problems, we covered MAE, MSE, RMSE, and the R-squared score. Then we learned how cross-validation, K-fold, and stratified K-fold help us evaluate models more reliably. Finally, we understood the relationship between bias, variance, underfitting, and overfitting. These concepts are essential for building machine learning models that perform well in the real world. In the next lesson, we'll begin Phase 3, where we'll start exploring the core machine learning algorithms themselves. If you found this lesson helpful, don't forget to like the video, subscribe to the channel, and share it with anyone learning machine learning. I'll see you in the next lesson.